All right, so last time we set up the problem. We're going to try to fit a line to this data. And we're seeing this data in batches of 5 points at a time. So here's an example batch, 1, 2, 3, 4, 5, these different points here. And now we're going to try to make a line that fits those. So how are we going to define that line? Well, this is a linear model that is going to take one input feature, the x position, and map it to one output feature, the y position. So we're going to fill in, we're going to create a neural net.linear model with one input feature and one output feature. That corresponds to the shapes that we saw in x batch and y batch. So if we ask for the shape of x batch, we saw 5 points, these 5 points here, and each one of them has one feature. This number 1 is going to have to match with that number in features of the first layer in our model. So far, our model is only a single layer, so this is fine. But when we have more layers of the model, all of the corresponding dimensions are going to need to match. Likewise, the output, the shape of the output, is also 5 by 1. So each one of these 5 points in the batch has one output feature. So it's pretty conventional that you'll have one output feature, maybe two or something in a model when we're doing a regression model. In a classification model, you'll have one output feature for each class that you want to predict. Strictly speaking, you only need classes -1 of those, so a binary classification only actually needs one class, but usually we give the full range of classes anyway. Except in binary classification. But we'll see binary classification soon enough. Let's focus on regression right now. So we've matched the shapes of the input and output data sets. So we have one feature to one feature. Now what about bias? Do we need a bias in this model? What's the bias correspond to? So the linear model here, let's just actually look at the contextual help. There's various ways of doing this depending on what you're using. Sometimes you can do Shift Tab on here to view this documentation also. So just click somewhere in the object and object's name and press Shift Tab, and it will bring up the docs there. What I've done here is put it on the side, just in this Jupyter Lab version here. So it's going to do a linear transformation, y equals x times a transpose. So that's just a fancy way of saying this is what the weights are going to be. And this transpose is sort of an internal detail. We could have stored them the other way around. Plus b. So if bias is set to false, the layer will not learn an additive bias. So it's going to turn off this b. Do we want a b? Yes, we do. Because remember, the model that we are trying to fit is y equals mx plus b. In this case, the weight matrix is just going to be a single value, and our bias is also going to be a single value. But still, we can use that general machinery. And then when we have more than one feature, we'll be able to use that equally well. So we're going to set bias to be true over here. Now we've got a model. So what we're going to do is we're going to check that we got these features right, these dimensions right. So if I say I'm going to call the model, and a model is just a function. It's a special kind of function that can learn its parameters, but it behaves just like a function. Let's give it our batch. So we have our x batch, and that's going to give us a tensor of y outputs. So here is what the model predicted for an x of 0.999. It predicted 0.04. Now we know that that's actually a pretty bad prediction. We'll plot it in a moment. But fortunately, since this is a model, we've got a grad function here. It's keeping track of the gradients. So inside of this model, we've already got two things called parameters, which are basically a tensor with requires grad true, and it's got one little extra kind of tag on it to say, hey, this is a parameter of the model. But all you really need to know is that this is a parameter just like our weights parameter over here in the original linear regression. Notice that this was a tensor with one item in it. and we required grad true. This is a tensor with one item in it. It's got an extra surrounding. It's two-dimensional instead of one-dimensional, and that's so that we can have both more input features and more output features, more than just one. So in general, this is going to be a matrix that maps from input features to output features. So we can also look at the model's bias. I'm going to change that here, and now this is a single number. It's also one number that's a bias for each output feature. Okay, so we've looked at that, and we've seen how to make predictions. It seems like these are pretty bad predictions. Let's look at them and then evaluate how they did. So I'm just using these utility functions that we defined up top, and we're going to plot what this model looks like. So it's just evaluating the model at every x, and that looks pretty bad. That's clearly not a good fit line for this data. It's sloping down. So how can we measure that? We use the mean squared error just like we did in the previous notebook. So here we evaluated the mean squared error as y predicted minus y true, squared mean. And we'll do that again here, y predicted minus y true. Now the true thing here is one value from the batch. So this is just going to be these 5 data points. We're not looking at the entire data set all at once, but still the same mechanism here. So 4.2759 units squared. So let's try to do that using the mean squared error loss module. So the syntax for this is going to be just like the linear layer here. So we're going to need to instantiate it, nn.msc loss. And we need to remember to call it as a function. So now we have a loss function. So we call it to make an instance of this class. MSC loss is a class, and we're making an instance of it. Why is it? Because it's able to give some extra parameters, like to perhaps not take the mean if you want it not to. But we'll take the mean, it's fine. So we'll just use the default parameters. And now we want to evaluate that loss on the example batch. So what we'll do, I'm going to take the erratum here from our notebook here. Yeah, I'll just pull that right in here. This note should read this. So we're going to evaluate this loss on the example batch that we made. So we have an X batch and Y batch. Let's call it, call our loss function. And we're going to need the model outputs first. So that's the Y pred, and then the predictions, or then the correct outputs, Y true. So we called that Y batch because these are the true outputs for this batch. So we run that and we get exactly the same thing. If we'd instead tried to do it on the full Y true, we would have gotten a, hey, dimensionality mismatch, because, yeah, size of the tensor A, so tensor A was 5, tensor B was 500 data points. Oops, you'll unfortunately see a lot of these, so don't get too afraid by that. Just say, okay, what are the dimensions of the two things in here? You can always just check, well, what's Y pred's shape and what's Y true's shape? And then what are these numbers? These numbers should match up. They don't. So we mean Y batch, because the Y batch has a compatible shape. Okay, so what we've just done is replicated the modeling and the loss computation that we did in our previous notebook, now using PyTorch models. So in our next little walkthrough, we'll construct a learner that will let us use these building blocks to now, in just a couple lines, fit this simple model to all of the data. Come right back.